So my lab produces smart data out of raw data using semantic technologies, and I will show you a little bit what I mean by that during the next like 15 to 20 minutes. So this is what you all read. It's the summary of the workshop, and what I like particularly about that, maybe hard to read now here due to the light, but what it says is that the workshop is about the usage of data, particularly big data, based on behavioral models, on behavioral data. And what I really love about the text is that it comes with this warning saying, but be careful because you will use this behavioral data to draw some inferences. And this is always a dangerous step, and that's exactly what I like you to show to you. So talking about data and big data and smart data and whatever buzzword is on your mind, one of the interesting things to notice is how we think about data. So how do people think about data who really want to sell you analytics products, want to tell you that machine learning and mining techniques are the future of how we are going to understand domains, say transportation science? IBM is one of those. And they come up with this beautiful set of posters and demos and videos. You can find them all online. They are really beautifully made. And they say that big data is the new natural resource, right? So I hope you digest that for a second before I move to the next slide. So big data, the new natural resource. Well, let's make a reality check here with this analogy. So a natural resource is natural. Not sure about data, but let's skip this one. So typically natural resources are exhaustive. So there are some exceptions like, radiation from the sun. But in most cases you can use them up. Again, not a very good analogy here. Then many of them are renewable, for instance. Also not a very good analogy here, but now comes the point. Natural resources are consumed in the process. Data is not. I can use the same data, send it out 100,000 of times, and it's still exactly the same data. It doesn't get bad. I don't use it up. So the only part that I can agree of here is that it's actually a building block. So natural resources and data may be building blocks for something else. But otherwise, I think this is a pretty broken analogy. Why is this so important, and why is this a start for my talk? Because the problem here is that if we don't even know what data is, if we don't even understand what data is, how should we try to make sense out of that? And what we do in my research lab is we try to make data smart so that all further applications and machine learning processes, statistical techniques or whatnot you would like to use are easier to use, and the data assists you by telling you, this is what you can do with me, this is what you probably should do with me, and if you do this and this with me, well, you will get patterns, I promise, but they will not mean anything. And I would like to show you this in effect.
From an information perspective,
yes.
Once you process it, already you've actually consumed it. So the value that remains is now less than a sense.
Oh, I would love to have this discussion in a minute, because look, the base data stays the same. I agree with you. You take the data, you process it, and this typically, say, enlarges or reduces depending on what you were to do, something like, for instance, information entropy. But the raw data that you had before is still there. And I can give the data to somebody else, right? This is why companies like Google, Apple, and so forth, okay, this is Videotape, I'm not going there. This is why they make so much money, Okay, so let's look at one example, and I hope me playing around with the slides until the last second will still make this work. No, it doesn't. So let me move this over here. Where's the cursor now? Here we go. So what you see here is data from a social network, a location-based social network called Foursquare. And what they did here is they show you what they call the pulse of a city. What they are doing, they collected 1 year worth of data, aggregated all those data, and then each of the single points that you see here, and please look what's going to happen here at 4 a.m. in like 3 hours, shows you geosocial check-ins. Look at what's happening here at 4 a.m. So each single dot is a geosocial check-in, and each linear feature, each line connection is the relation between one check-in of the person and the next check-in of that person. And check-in, if this term is not familiar with you, just means that a certain user of such a location-based social network decided to announce to all of us that this person just visited this place. Why people do this is an entirely different story. Let me play that for you again. And here you have the types of places. For instance, like 10 a.m., the food is trending, so to speak, and the shops, a little bit of the travel. Now it's 2 p.m., the great outdoors play a role now, maybe a little bit more shopping, and then it gets towards the evening and you see the pattern changing. So the nightlife spots are lighted up and so forth and so forth. And now again at 4 a.m. you will see this mysterious blob moving here. So you can look at this a couple of times, and you are actually the experts in this data, so you understand this data well better than me. But the first thing we saw in my lab was, well, what exactly does it mean we took millions of data worth a year, that's what they say, and aggregated it, and this is the pulse of San Francisco. So this is exactly what they wrote here. Well, there are several problems with that pulse of San Francisco. So first of all, to come directly to this point, it's aggregated to a single day. So whatever pattern you will see in that, this pattern actually doesn't mean much, because we know that people behave differently during different days of the week, right? They behave differently during the weekdays than during the weekends. They behave differently during holidays than during work days, during seasons and so forth and so forth. So taking all the data and making such sort of virtual day, not sure exactly what that means. And then there are, of course, other things with that, like it's not interactive, it's just a video clip. You can't click on those places, you can't learn about them. It has a fixed geographic scale, so you cannot see other parts of the city. But from my point as a knowledge engineer, as working in the area of semantics, what is more interesting is that they did a certain classification. So all those places that can be visited are categorized into 421 types of points of interest, and then they show you like 9 super categories. So they always had to make some assumptions what to group into those super categories. And if you group 400 subclasses into 9 superclasses, this will always introduce some sort of ambiguity and some sort of randomness in the process. And it's just interesting to see how that played out. We don't know, that's the problem with data from such company, what exactly they did and how they did it, but the results are a little bit surprising. For instance, cemeteries are categorized under the great outdoors, and there are other, well, it's not exactly wrong, it's a little bit unusual maybe. And then there's also this category that is called professional and other category. What does it mean that other category is trending right now or something like that, right? And then what they also didn't do is they didn't address the issue that, well, this is socially contributed data, so many people tag castles in San Francisco and LA. There are no castles there, it's just, the slogan, my home is my castle, and they tag their own houses as being castles. So what we wanted to do is we wanted to come up with our own version of that, and I will show you that in like 5 minutes, but be more informed by, on the one side, really mining the data using machine learning techniques, and on the other side, using classical approaches from semantic engineering, like from the field of artificial intelligence. So one thing we are doing since like 3 years now, or maybe 4 or 5 years, is an interesting analogy that I would like to present to you. So you are all familiar, or many of you may be familiar with spectral signatures. So the idea that we can learn about the land use, for instance, we can even learn about distant planets, which is very fascinating to me, by particular combinations of emittance, reflectance, and absorption of electromagnetic radiation of wavelengths of a certain length, and this is what we call bands. And jointly those bands form unique signatures so that you can tell apart certain types of features. So for instance, you need only one band of wavelengths to tell apart paving concrete from bare brick, but you need more bands because the visible band wouldn't be enough over here, sorry, to tell apart conifers from deciduous trees. But if you have many of those bands, you will be able to uniquely identify a type of feature, which is a very powerful idea. So we took this idea that I think revolutionized remote sensing, and especially the idea of sharing these signatures, and we brought in semantics to the mix, so models about how we engineer knowledge and how we know what's there, and came up with our own analogy. So we have semantic signatures. They could be temporal signatures, they can be thematic signatures, they can be spatial signatures, and all of those can be mined or extracted from data or learned, and then they can be combined, all those bands, to understand features on a micro, meso, or macro scale. I will mostly focus on the micro scale today, but I will show you some examples of meso and macro scale as well. And once we did this, and we did this now for hundreds of bands and for hundreds of types of features over the last years, you can use them in really amazing ways for data categorization, deduplication, enrichment, cleaning, visualization, exploration, and so forth and so forth. And right now we are studying their regional effects, so how stable such semantic signatures are over space and place. But let me first show you some of those signatures. So here's a summary page. As we are geographic information scientists, we group them into geospatial bands, temporal bands, and thematic bands. Not saying this is the only way to group them, but for us it's a very natural way to think about space and place. So we have, for the geospatial bands, we have based versions of Ripley's K. We have an own measure that we did called the J measure, a second own measure that we did, the D0. We have average nearest neighbor distance and so forth. For the temporal bands, we have hour bands, day bands, we're working on seasonal bands and so forth. And for the thematic bands, we use, for instance, topic mining and topic modeling techniques like latent directly allocation or term frequency, inverse document frequency as an alternative techniques. And those give you fine-grained approaches to understand when people visit places, those are the temporal signatures. What they say about places, those are the thematic signatures, and how those places are configured with respect to each other. And always keep in mind, we are talking about the type level, not one pub, but pubs, not one school, but schools, and so forth. So let's look at some of them. So for instance, for the thematic signatures, we use this very powerful idea that non-geographic terms are still geo-indicative. So if I would say beach, dolphins, beach volleyball, then I'm not in the Rockies. If I would say snow, very cold, a lot of traffic, I would be in New York, for instance, right? So clearly you are less or more likely to utter certain terms depending on where you are. And this creates a density surface which tells us for each term in the English language, and that's what we did, its likelihood on a fine-grained tessellation of the Earth's surface, where you most likely would be uttering those terms or not. So here you see topic 312, which talks, for instance, about and they are stamped. Don't wonder why they look so different. So industry, factory, company, manufacturing, production, employment, a worker, business development, machinery, and so forth and so forth. And you see the density peaks here. This is in fact an interactive version, and this is just a screenshot. And here you see a topic about waterfalls, rivers, mountains, hikes, pools, views, scenic, geography, and so forth, and you see a very different pattern. So what we know is that we can come up with this density surface of human expressions, and once we have that, we can actually order them and say that if you are talking about a type, a city, then most likely you're talking about those topics in decaying order, and if you talk about towns, you see there's an overlap in those because cities and towns are actually a little bit alike, but mountains would have very different topics that you would discuss, and then you can again plot them and see the various patterns like the Rockies and the Pennies and the Himalayas and the Andes and so forth and so forth. So you could also use the very same idea to see which differences you can really make in your data set, because we're introducing so many feature types, and in most cases they are not supported by the data. So for instance, you can easily tell apart mountains from not mountain features. You can easily tell apart power stations from not power station features. But it's very hard to tell apart city from town features, and that's for good reasons. I'm not going into details here, but for instance, in the state of California, city and town by law are the very same, while in Pennsylvania you just have one single town, Bloomsburg, for historic reasons. So it's really true what the data is telling us here. So in terms of the temporal signatures, you can play the same game. You can say, let's look at types of places, wineries, nightclubs, football stadiums, airports, and see when people visit them during the day, and in this case, for instance, during the week. And you will see that stadiums differ clearly from, let's say, airports or wineries, but you could see that wineries and nightclubs, they're mostly visited during the weekends. So you may say, we can't really tell them apart. But if we add a new band, in this case the hour band, then you see that wineries are visited during the daytime, like 10 to, let's say, 8, and nightclubs clearly during the nights. You can then suddenly tell them apart. You can combine this. We did this for 400-something places, mined of really millions and millions of check-ins and hundreds, thousands of places. So they are pretty robust by now. For the spatial bands, you can do a similar trick, but now you say, how likely are places of a given type co-occur with places of the same or a similar type? And this is an example for London, a study that we published like 4 years ago, showing you post offices and post office-like places versus bar and bar-like places. Well, it's, it involves students. It has to do something with drinking. So, and here you see the degree of similarity. What you can easily see is that bars and bar-like features clump together, while post offices obviously don't. And you may say, that's a triviality. How would this be important for data cleaning, for instance? So here we came up with a new statistical measure for measuring exactly those effects that show you that bars tend to co-occur with bar-like features in the close neighborhood of them, while if you have a post office, it's very likely that the buildings nearby are different, are in fact substantially different from post offices. And now imagine you have volunteer geographic information, and a user adds a new data item, let's say a new place, or you want to merge different data sources. And in fact, we have to do a lot of merging in my lab to come up with very rich data sets. Then let's say I have a post office here, and a user wants to add a new post office 50 meters away. Or I'm conflating two places, the addresses don't match exactly, and I have two post offices 50 meters away. How likely is that? It's very, very unlikely. It's likely for pubs, but if there's a post office and you want to add one next door to it, it's most likely not a post office, it's a duplicate of what you already had in the data. So what we can do with that is we can, now that I introduced you to the semantic signatures and how we model them and how we use them, we can redo what Foursquare did for their pulse of a city, and we can come up with our own pulse of a city. And I'm going to show you a live demo here. I always tell my students that live demos are something that you should never do, but for some reason I just can't stop doing them. Okay, if this is all going to crash, then I have a backup. So the problem is that the projector has a very low resolution, and I'm on Wi-Fi here, so please don't expect this to be particularly pretty. You can go on poipulse.com and do it yourself. So what you see here, and unfortunately there's a lot of light on that screen. Is there some way to turn out the light, turn off the light for just a second? I think it's probably more this one. Is it better now? Okay, thanks. So, well, it's still not really a good one, but don't worry. So all you see here is, in fact, 200,000 points of interest. This just looks like streets to you. In fact, the points of interest are just so dense. And we see them here at Sunday, 12 a.m. And what we can do now is we can advance our by hour, by hour, by hour, by hour, and LA is falling asleep, and now it's waking up again, 10 a.m., 11 a.m., and so forth and so forth. But this is just all the data. It doesn't tell us what's really going on here. So you can zoom in to any particular place, and now suddenly we get another categorization. And in contrast to the Foursquare categorization that I showed you before, this categorization is modeled using all the signatures that I showed you before, and then using support vector machines. So we think the categorization makes more sense. You can enable and disable categories, so it's interactive. You can disable this category, enable it. Now I zoomed in accidentally. And what you can see is the pulse of the city. For instance, you will see that while time advances, certain places will be less prominent than others. What you can further do is you can zoom in even further. Let's take here the Santa Monica region. Okay, it will load a little bit. This is the Wi-Fi problem. Okay, let's go here. And you can see which places and which types of places are very active on the typical Sunday 6 p.m. And keep in mind that this is default behavior. This is aggregated from how people speak about places, how people interact with other places, how places interact with other places, when people visit places. And this creates this very powerful default behavior, and some of that is very stable across geographic regions. Others is not. As we said, we are just doing research on that. But you can see that at this 6 p.m., certain places are more likely to be visited than other places. You see the Santa Monica Pier, and then you can go over all those places and go beyond the binary categorization. And for instance, you can go on, say, this place, and this is a concert hall, or you can go on this place, this is general entertainment, and you can go on this place, or whatever place you like, say this one here, nightlife places, or again, a concert hall, tennis court, and so forth and so forth. And what you see here, and I think this is one of the nice features about that, is that suddenly you don't have this binary distribution anymore, but you learn more about the place. So for instance, there's a coffee shop here, and you can see that the coffee shop in our classification is like 22% commercial service, then it's part of the community infrastructure, then it's part of retail, education and health, and so forth, depending on the place where you are. So this is a church. This is, for instance, well, you see how it works, right? Unfortunately, the screen resolution is a bit, but this is a comedy club, which is mostly entertaining and nightlife, but it's also an attraction in eating and dining and so forth. But this is all, as I said, the default behavior. And if I would advance through time, you would see that those patterns will be changing. It gets towards the evening, so the nightclubs are what's still visited, and so forth and so forth. So this is the default behavior, and now I would like to see what is actually going on right now and how is it differing from the default behavior. This is then the part that talks about anomaly detection, right? So I can't do this on this scale because all this publicly available data, Foursquare, Twitter, Yelp, Facebook, whatever, they have API limits. They don't give me all the data. So I need this model, this default model that we are actually allowed to store because it's in line with their usage restrictions to model the pulse of a city. But once I zoom into a specific level, let's say here, I'm actually at a range where I can get real data. So I can activate the burst mode, and the second I do this, it will switch to today and exactly the hour of today, Friday 11. And what it does right now, it pulls tweets as we speak. Those are individual tweets, so people are just sending out messages over there, and you can connect many other sources if you like. But what this does, and it may take some seconds, it will actually check not just our probabilistic model where people are, but it will check real check-ins of real people, and don't wonder about why the numbers will be pretty low. It's just really people who checked in right now at a place at Foursquare. And of course, Foursquare has a limited user base. It's 11 a.m. We are checking in who's there right now, not in 2 hours or an hour ago. So don't expect that there would be like 100 people on the pier, which will be the case. We'll only show those who are really checked in using their mobile device. And as you can see here, there's just a new tweet that appeared. Okay, and you can see here, for instance, that there are 3 people who checked in at that particular pier here, for instance, and there's one person at that grocery store, and there's one person here at the mall, and two persons staying here at the hotel. So we disabled, I can enable the residential buildings here, but so then you have some more over here and it changes the pattern, and now there's a little bit of a rendering problem, but I can do so. Okay, and that's everything I had to say. So starting with the limitations of the Foursquare polypulse, which was still very inspiring, but you had this aggregated virtual day, you couldn't really interact with that. We came up with a data-driven approach that mines from many different sources the data, aggregates them, combines them into those semantic signatures. We use them for many other tasks. In this case, to give you this access to the polypulse, which shows you the default behavior of a city, when is which part of the city visited, yada. But you can also go back to the default mode and see, to the burst mode and see what's going on right now. Thank you very much.
I wonder if we can cluster, if you will, those people that are actually using Foursquare or something, some tool like that, as compared to others, especially within their context of their spatial behavior.
Absolutely, and the degree to which we can do this is absolutely shocking. So we all know that the data is biased, but I think sometimes we don't see how biased in fact it is. So let me first say how we get around this problem. We get around this problem by aggregating really millions of check-ins, millions and millions of check-ins to hundreds of thousands of places. And then it's true that people go to the bakery in the morning and to nightlife clubs in the evening, and that's what we really need here, and that's what makes this work so nicely. For another study that we did, we took GPS coordinates and we did something that is called geolocating a user. So intuitively, knowing where a user is in terms of space is not really interesting for companies like Google or Apple or Foursquare. They want to know which place you are. Let me give you a trivial example. If I'm standing near a food truck, that doesn't mean anything. If I'm at a food truck, I checked in, so to speak, I'm at a place, not a space, a food truck, then I'm most likely getting food there, right? So they take your device location and then they try to say at which place you are. And interestingly, Google does this based on distance only. So what we did based on the temporal signatures, we morphed the space using the temporal check-in probability, and we can show that this increases Google's result by about 30% in terms of accuracy of finding out where you really are in terms of your device spatial location to the placial location. And here comes the interesting part. We also wanted to advance on Foursquare's baseline. They also have their own service, so we thought, okay, and now we are going to outsmart them as well. But unfortunately, we also took the user base to test that. And it turns out the best prediction where the next Foursquare user is going is to see where the last ones went. So the data is biased to a degree that the strongest indicator is not your location, your exact location. It's not the time of the day. It's not what we were saying, where you went before, but whether this is a place where other Foursquare users go. So I absolutely agree. It's quite amazing, and you can clearly tell those people apart. Thanks for the question.
One of the items we want to do is validate if our data is right, but also if we can complement it with how these businesses are used for entertainment, etc. We also have 18 million people of the same region, the entire schedule they do. So when I look at what you're doing and when I look at what we are doing, I'm thinking, oh, can I use Janowicz data to validate? Can I use it to fuse the data and come up with better knowledge? And the key indicator, at least in the activity-based models that we are doing right now, is human interaction. So the social network data can tell you with whom you do activities and who else is with you, not because you're doing an activity, but they just happen. How do we go there? How do we get to the next level of understanding of what people do?
Let me make a provocative statement here. I'm going to say that if you would give me your database, I could tell you which places have changed ownership in business, because the signatures coming from those places will change. If it was a car shop before and now it's a bakery, then the check-in behavior will change, how people talk about that will change, and so forth and so forth. I would really love to put this to the test. So absolutely, this afternoon. Yeah. And the second thing is a little bit about redoing these studies. You know that we did a paper with Song Gao sitting here being the main author, where we took transportation studies that are very heavily in terms of the money you have to invest, they take a long time, and we just collected tweets and we redid this study with a very high, very high strong positive correlation. And the funny thing is that at the beginning, we didn't even realize what the potential of that, so we put it in a short paper, sent it to some conference, and then after that, we only understood, oh, well, this is actually, we saved somebody some $1 million. So I think it's amazing what you can do with data, but big warning, you will always find some patterns. Be very careful what you draw in terms of inferences, and I think the Foursquare example is a good one. You need smart data, you need semantics to model what those places are. You need strong similarity metrics between those places, types of places, and stuff like that. Okay, thank you very much.